Now today let's learn another characteristic or property that should be satisfied by a good estimator, or the desirable property that a good estimate should have is sufficiency, one of the desirable properties. So an estimate of a parameter theta, usually an estimate of a parameter theta is taken as t, is called a sufficient estimate if it contains all the information about theta that is contained in the sample. Now let t dash be any other estimate of theta. Now there can be more than one estimate for the parameter theta. Now if suppose there is another estimate other than t, so usually we were dealing with t only, but if there is another estimate other than t, say t dash, then the joint PDF of t and t dash. Okay, let's consider this p of t comma t dash as the joint PDF. Okay, now and also consider that the conditional probability of t dash given t, consider this, and if this is independent of theta. Now if this PDF it does not have any terms regarding theta, for all t dash we say that t is a sufficient estimate of theta. Okay, now all these things will be a bit more clear when we come to a problem. So before moving on to a problem, we have to learn about the factorization theorem or Neyman factorization theorem. So the necessary and sufficient condition for an estimate of the parameter theta to be sufficient is given by Neyman, and this is very useful in examining whether a given estimate is sufficient for theta or not. So let's have a look. So this factorization theorem or the Neyman factorization condition for checking whether the estimate is sufficient or not is used when we encounter with some real problems. So let's see, let x1, x2, etc. xn be a sample which is taken from a population with PDF fx theta. Now the joint PDF of the sample, is usually called as the likelihood of the sample, and it is denoted by L of x1, x2, etc. xn comma theta. So what is it? The joint PDF of the sample is usually called as what? The likelihood of the sample, and it is denoted by L of x1, x2, etc. xn comma theta, which is equal to, it is the product of all the what density function of that individual samples, that is f of x1 comma theta multiplied by f of x2 comma theta, etc. f of, since there are n, so it is f of xn comma theta. Okay, now here if t is a statistics that is taken into consideration, if t is a statistics, and we say that then t is a sufficient estimate of theta if and only if, so there is a condition, if and only if if it is possible to write the likelihood function that is just given above in the terms of L1 t theta L2 multiplied by L2 of x1, x2, etc. xn. Now what does this mean? The whole likelihood function you should be able to represent in this format. Only then we can say that t is a sufficient estimate of theta. Now what does L1 t theta represent? Now L1 t theta is actually a function, it is a likelihood function, a function of t, that is the statistic and the parameter alone. And what about L2? L2 is something which is independent of theta. L2 x1, this particular function L2 x1 x2 etc xn is independent of theta. If you are able to express the likelihood function in this manner, then we say that t is an estimate of theta. T is an estimate means T is a sufficient estimate of theta. Now we say that T contains all the information regarding theta. Okay, so let's see. Now we will move on to a problem, and we will just apply the factorization theorem, and let's see whether we can represent the whole thing in terms of your likelihood function, and whether we will check whether it satisfies the Neyman factorization theorem. Okay, so the problem 1 is regarding a normal distribution. We are taking a sample from a normal distribution. So just write down the question. Show that if sigma square is known, show that if sigma square is known, x bar is a sufficient estimate, x bar is a sufficient estimate of mu. Okay, comma, x bar and s square being the mean and variance, of a sample. Okay, now here we have to check whether x bar is a sufficient estimate of mu if sigma square is known, if sigma square is known. So let's move on to the solution. Now we know that the PDF of a normal, so it is clear that this is taken from a normal distribution, and and the sample and the samples are taken from a normal distribution. So our PDF, so what is the PDF of a normal distribution? 1 by sigma root 2 pi e raised to minus x minus mu the whole square divided by 2 sigma square. This is the PDF of a normal distribution. Now we are going to apply the factorization theorem. Okay, so when we apply the factorization theorem, let's see, so what is our aim? Our aim is to find whether we can represent this likelihood function in terms of two functions. One function which is which have the statistic and the parameter, another function which should be independent of the parameter. So first of all, let's find out the likelihood function. So as I said before, the likelihood function is usually represented as what? L of x1, x2, etc., xn, and this is equal to what? 1 by, so usually what is the general formula? First we will write the general formula, then x1, you just write the parameters mu comma sigma, in this case it is mu comma sigma, multiplied by f2 of x2 mu comma sigma, multiplied etc. Sorry, there is no f2 over here, it is f of x2 mu comma sigma multiplied by f of x3 mu comma sigma, etc. Finally you have f of xn mu comma sigma. Okay, now how will you expand this? When you substitute this, what will you get? L of x1 x2 etc xn comma mu comma sigma is equal to, what is the f of x1 mu comma sigma? 1 by sigma root 2 by e raised to minus of x1 minus mu the whole square divided by 2 sigma square multiplied by, what is f of x2 mu comma sigma? 1 by sigma root 2 pi e raised to minus of x2 minus mu the whole square divided by 2 sigma square multiplied by etc. multiplied by 1 by sigma root 2 pi e raised to minus xn minus mu the whole square divided by 2 sigma square. Okay, now this is equal to, you have n times this constant, that is 1 by sigma root 2 pi, right? So I'm going to club that. So what I get is 1 by sigma, since it is n times, it is the whole raised to n multiplied by e raised to minus, since e raised to, these are all over here, I mean the powers over here, I'm going to add this up. So when I add it up, what I get is minus 1 by 2 sigma square summation xi minus mu the whole square. Okay, so this is what I get. Now this is equal to, I just have to represent this in terms of what. So see, my question, in my question it is clear that whether I will so it is clear that I have to check whether x bar is a sufficient estimate of mu. So the problem over here is I don't have any x bar in this following equation. So what I'm going to do is I'm going to take now this term, okay, this term, and I'm going to expand it. So while expanding it, what I'm going to do is summation xi minus mu the whole square. I'm going to introduce an x bar over here, xi minus x bar plus x bar minus mu the whole square. Okay, so this adjustment is done over here, which is equal to summation xi minus x bar. Fine, I hope sorry, to rearrange the terms, xi minus x bar and plus x bar minus mu, fine, the whole square. So this is now in terms of a plus b the whole square. Now this is equal to summation summation xi minus x bar the whole square, okay, the whole square plus 2 into, there will be a middle term over here, but since I hope you all know why that is up here, so I don't have to explain it again and again. Plus our third term will be what, x bar minus mu the whole square. Now what I'm going to do is I'm going to take the summation inside. So when I take the summation inside, I get what, this term, I mean the first term. What is the first term? It is nothing but ns square, right, plus what is this? This is n into x bar minus mu the whole square. Okay, so I hope instead of this you can write this term, and you can take the uh, n outside, or you can just keep it like that itself. So this is equal to 1 by sigma root 2 pi the whole raised to n multiplied by e raised to minus ns square divided by 2 sigma square. Okay, I'm going to split this up, multiplied by e raised to minus n x bar minus mu the whole square divided by 2 sigma square. Okay, now if you join this you will get this itself, right? I haven't written a step over here, just give a little thought about this, which is equal to now here you can just rearrange these terms a bit more in a way such that it satisfies the factorization theorem. So what I'm going to do now is I'm going to write this as e raised to minus n into x bar minus mu the whole square divided by 2 sigma square multiplied by 1 by sigma root 2 pi the whole raised to n e raised to minus s square divided by 2 sigma square. So this is your L1, and L1 is what? L1 is a function which has your estimate which is associated with what? Your parameter, and also the is a function of your statistics x bar and also your parameters, that is mu and sigma over here. Fine, so this is your L1. And what about this? Do you have any statistic involved over here? No. So this is independent, or independent of your parameter also. So parameter mu, you don't have your mu over here, so it is independent. Now here you have your parameter which is of concern, that is mu. Okay, now see, in a normal distribution sigma is also your parameter, but our question is you have to check whether x bar is a sufficient estimate of mu. Fine, so here mu is involved, but in this part mu is not involved. Okay, so we are only concerned with mu. Sigma is there, but that's okay. Now L2, what is L2? L2 is independent of mu. You don't have mu over here, so this is L2. So again, we can see that we can express this likelihood function in terms of L1 and L2. Fine, therefore we can say that x bar is a sufficient estimate of mu.